Okay, 1.2, roots and radicals, and these are sometimes called surds. Okay. So we're going to go through two things, simplifying radicals and rationalizing denominators. We're going to briefly look at rationalizing a numerator, which is kind of a funky thing, but we'll go over it real quick. Looking at this statement right here, if I'm looking at the square root of A is called the radicand. Okay. And the whole thing is called the radical. Right. So we've got some rules here that we've worked with lots and lots before. So you can take this composite one and you can break it up into the nth root of A times the nth root of B. Or here where we're looking at a fraction, you can always break it up into the nth root of A over the nth root of B. And so long as these n's are the same, right, you can go back to this form. So this works either way, back and forth. Okay, so I'm going to put these arrows on here to remind myself that it works both ways. We're just going to go through some examples now. So 2 over the square root of 10, well, can we rationalize the denominator? Because remember, having a square root in the denominator is considered poor grammar in math. So there's a couple of different things we can do. In this instance here, it makes most sense to multiply by the same number because what's going to cancel that square root out will be another square root. And of course, we can't just haphazardly multiply by whatever we want, but we can do it sneaky if we use one of those ones in a funny form. So root 10 times root 10 is just going to be 10. 2 times the square root of 10. Nothing new here, and then we're going to reduce the 10 and the 2 because they're both now to the 1 power, so we can reduce that. So I have 1, which we don't have to write, times the square root of 10 over 2 goes into 2 once, 2 goes into 10 5 times, so root 10 over 5. Now some people might be tempted to say, well, 10 and 5 reduce. Yes, that's true, but this isn't just 10, right? This isn't a 10. Technically, this is the square root of 10. So this is 3 point something over 5, and so we can't simplify that. They both have to be under the same radical. So if this were a square root and this were a cube root, you still couldn't do it. They both have to be under a square root to make that work. For instance, right here, if I have root 5 here and root 35 there, well, those can reduce. So you can rewrite this as 3 times the square root of 5 over 35, which reduces to 1 over 7 in there. So this becomes 3 times the square root of 1 over the square root of 7. Well, cool, but I don't really know that that helped me all that much, but it's nice to think about, right? Kind of makes us think about things. So what I do still need to do here is rationalize the denominator. So I'm going to multiply by a sneaky 1 in the form of that root 7, because the square root of 7 times the square root of 7 is just 7. So now I don't need to write square root of 1 anymore because the square root of 1 is just 1. So now I have 3 root 7 over 7. Check real quick to see if these can reduce. Nope. Looks good. Okay. I'm going to look now kind of some trickier ones. Okay. This one has a polynomial in the denominator, right? Polynomial with a radical. Well, that's weird. How do we get rid of that? Well, if you remember back to when we did the difference of perfect squares, if I take a plus b times a minus b, your center terms cancel out when you multiply those together. So we use that technique. We're left with a squared minus b squared. We use that technique to help us eliminate any radicals being left in the denominator. So the conjugate, that's what this is called. We're going to be multiplying here. The conjugate, we all know what a great speller I am. The conjugate of 1 plus root 5 would be like the difference of perfect squares, 1 minus root 5. And then of course we can't just haphazardly multiply. We're using our sneaky ones. So look at our rule down here, or if you wanted to multiply it all out longhand, you could. But 1 times 1 is going to give us a denominator of 1 for that part. And then our AB is going to cancel out with our minus AB. So our center term is going to cancel out whenever we multiply our difference of perfect squares. So the same thing here, our AB term would multiply out. So AB, and then you would have minus the exact same thing, so it cancels out. So I'm going to have square root of 5 times square root of 5, which is just 5, and then it's going to be negative 5. Okay. So there goes a noisy motorcycle. 3 times the quantity in the numerator, 1 minus root 5. And then is there any further we can simplify this? Well, sure. We can write that as a number, right? That can be combined. So, of course, I'm running out of space here, so I'm going to come down here. 3 times the quantity 1 minus root 5 over 4 negative. We're going to pause there and take a little break.